So today we're going to be solving May-June 2021, paper 12. Question number 1 says, which statement about the Avogadro constant is correct? So the first thing we know about the Avogadro constant is it's 6.02 times 10 to the power 23, but it represents the number of something that you have. So it doesn't represent the mass at all. So we can easily eliminate A and B, right? We can easily eliminate A and B over here because it doesn't represent masses. And then it is a number of atoms in 1 mole of neon. Now 1 mole of neon is just atomic, right? It's a monoatomic molecule. So 1 mole of neon means 6.02 times 10 to the power of 23 atoms of neon. Is that Avogadro's number, right? So that means the answer over here is C, right? This is 1 mole of neon. And you can eliminate D as well, the number of atoms in 12 grams of any element. No, it's the number of atoms in 12 grams of carbon, but not of any element, because different elements, this many particles of different atoms will have different masses. So we're only talking about the number of atoms, not the, so this statement only applies to carbon, okay, not any element. It applies to carbon 12 specifically. Okay. Which equation represents the first ionization energy of iodine? The first ionization energy is the energy needed to remove 1 mole of electrons, right? 1 electron from each atom and 1 mole of gaseous atoms. So we're removing electrons from gaseous atoms. Which equation represents that? Only D represents that, right? Removing 1 electron from 1 atom, right? For 1 mole of gaseous atoms to form 1 mole of gaseous 1 plus ions. The structures represent 3 compounds, each with 4 carbon atoms per molecule. Which row is correct? Which has the lowest boiling point and which has the highest boiling point? All right, so let's actually think about which one has the lowest boiling point over here. And we're going to start by identifying the strongest intermolecular force in each of these. What's the strongest intermolecular force in this carboxylic acid? What's the strongest type of intermolecular force here? The strongest intermolecular force that we have in carboxylic acids is hydrogen bonding. What about Y? Do we have hydrogen bonding in Y? Do we have a hydrogen directly bonded to an oxygen or a nitrogen or a fluorine here? No, right? So here you just have permanent dipoles. That's your strongest intermolecular force, van der Waals forces. And what about this guy? What's the strongest type of force of attraction here? You have what type of a substance here? You have an ionic substance. So here you have ionic bonds, right? So then if I talk about Z, will it have the lowest boiling point or the highest boiling point? So because Z has ionic bonding, it has the highest boiling point, right? And which of these has the lowest boiling point? Y would have the lowest boiling point. So the answer over here is B. Question number 4. The structural formula of allene is shown. What are the approximate bond angles X, Y, and Z in a molecule of allene? The way they've shown the bonds over here isn't actually representative of the angle. So they're not showing the actual angle over here, okay? So you have to figure out based on your knowledge of shapes and hybridization. Now if you look at a carbon atom that's double bonded and it has a total of 3 atoms bonded to it, what type of hybridization is this for this carbon atom? What hybridization does this carbon atom have? It's sp2 hybridized, right? And it has 3 atoms around it and no lone pairs. So then what type of bond angle would you have here? You're trying to space out 3 atoms equally around the central carbon. So the bond angle here would be 120 degrees, okay? And that only leaves us with B and C already, okay? So that makes our life easier. What about this carbon? Again, it's the same type of carbon atom. So what's this bond angle? Again, it'll be 120 degrees. So then the answer over here is C, right? And you can verify this also if you want. You can look at the last carbon here. We have an sp3 carbon, right? Tetrahedral. So there's going to be 109.5 degree bond angles. Flask Q contains 5 decimeter cubes of helium at 12 kilopascals pressure. Flask R contains 10 decimeter cube of neon at 6 kilopascals of pressure. If the flasks are connected at constant temperature, what is the final pressure? So what we have over here is this. We have a 5 decimeter cube flask. and we have a 10 decimeter cube flask. Okay, and right now these flasks are not connected to each other. Okay, there's a stopper in between, right? And what we have over here is we have a 5 dm cube. Okay, and here you have 12 kilopascals of helium. Okay, and then in the other flask you have neon. Okay, you have a 10 decimeter cube flask at 6 kilopascals. Okay, now the easiest way to solve this is this. What we've done is we're actually opening the flasks. Okay, we're connecting the two flasks, and now what we're doing is we're allowing each of these gases to occupy 15 decimeter cube. Now if you look at helium, right, in 5 decimeter cube it had a partial pressure of, or it had a pressure of 12 kilopascals. Now in the new 15 dm cube flask, what is the partial pressure of helium? Can someone tell me? You've tripled the volume. You've gone from 5 decimeter cube to 15 decimeter cube. So can I say we know that pressure is inversely proportional to volume? So if I've tripled the volume, I'm going to have 1/3 the pressure, right? 3 times the volume means 1/3 the pressure. So can I say that the partial pressure of helium is 4 kilopascals now? We can also use P1 V1 is equal to P2 V2. And again, you're going to get 4 kilopascals. 3 times the volume, that means 1/3 the pressure. So that's the partial pressure of helium. Now what about neon? At 10 decimeter cube, 6 kilopascals. What if we add 15 decimeter cube? You Again, for neon also you can do the same thing. P1 V1 is equal to P2 V2, right? Initially you had 10 decimeter cube and 6 kilopascals. Now you have 15 decimeter cube. What's the new pressure? You multiplied the volume by 1.5, right? Initially you had 10 decimeter cube. Now the neon is occupying 15 decimeter cube. So 1.5 times the volume. That means 1.5 times lesser the pressure. So 1.5 times lesser. You multiply the volume by 1.5. That means you divide the pressure by 1.5, right? The pressure will be 10 times 6 divided by 15. So what's the partial pressure of neon then? Over here. The partial pressure of neon would also be 4 kilopascals, right? So now what do we have here? We have the partial pressure of neon as 4 kilopascals and the partial pressure of helium as 4 kilopascals. So what's the total pressure? It's the sum of the partial pressures, right? So the total pressure here would be 8 kilopascals. Question number 6 says, sodium chloride, water, and air represent 3 states of matter: solid, liquid, and gas. Which row is correct? Let's just go with sodium chloride first. Part A says particles are held in a rigid structure. For sodium chloride, is that true? This is obviously true because we have a solid lattice, right? Are particles ever stationary, or are they always moving or vibrating? Are particles ever stationary? Particles are always moving, okay? Particles are never stationary, so you can always eliminate B and C, right? Kinetic particle theory, if you guys remember, right? Particles will always have some sort of motion. They could be vibrating in the solid structure, but there'll always be a little bit of movement, right? So they're never stationary. And is sodium chloride malleable, or is it resistant to change in shape? We know that sodium chloride is brittle, right? It can't be molded. It's not like a metal, for example. So it is resistant to change in shape. So now we're only looking at options A and D. Now, if you look at water, water is a liquid. Is water easily compressed? Are liquids compressible easily? No, right? Liquids cannot easily be compressed. So therefore, water is not compressible, and that leaves us with option D. It cannot easily be compressed. And we know that air can easily be compressed, right? It's a gas. So the answer here is D. The reaction pathway diagram for the catalyzed reaction and the uncatalyzed reaction between N2 and H2 is shown. Which letter represents the activation energy? Which letter represents the activation energy for the first step in the decomposition of NH3 in the presence of a catalyst? So we know in this energy profile diagram, right, this particular curve, the one on top, represents the reaction in the absence of a catalyst. With the catalyst, the activation energy is lower, right? So this is the uncatalyzed reaction, uncatalyzed, right? And this is the one with the catalyst. Now, So first of all, we're only concerned with this one over here. Now, when we talk about the first step in the decomposition of ammonia, we're talking about the backward reaction. We're talking about this reaction going from ammonia to nitrogen and hydrogen, right? That's the decomposition of ammonia. What's the activation energy for the first step in the decomposition? So if we're going backwards from right to left, what's the activation energy for the first step? The activation energy is D. Okay, so the answer here is D. Nitrogen and oxygen can react together to form nitrogen monoxide. What is the bond energy of the bond between the atoms in NO? Now over here, we're going to use bond energies. Okay, so the bond energy for nitrogen is 944 kilojoules per mole, okay, in a nitrogen molecule. And for oxygen, it is 496 kilojoules per mole. Now, does anyone remember how do we calculate the enthalpy change if they've given us bond energy data? So they've given us the enthalpy change over here, and they've also given us the bond energies, right? For nitrogen and oxygen, we have to find the bond energy over here, the NO bond energy, right? And we know that the enthalpy change of a reaction, in terms of bond energies is the bond energies of the bonds broken minus the bonds formed, right? Or you could say it is the bond energy of the reactants minus the bond energy of the products, right? This is the reactants and this is the products. Now, what we have over here is, we talk about the bonds broken. We're breaking 1 mole of nitrogen bonds, right? So that is 944. We're breaking 1 mole of oxygen double bond, so that's 496. And we're forming 2 moles of these bonds, right? One NO molecule has 1 NO bond, and we're trying to form 2 of these. So what we have is, we have 2x over here. Sorry, minus 2x over here, right? Since we're subtracting the bonds formed. So that'll be minus 2x, and this is equal to 180. Okay, and what that gives us is we get 2x is equal to 1260, and that implies that x is equal to 630 kilojoules per mole. Okay, so the answer over here is A, 630 kilojoules per mole. The equation for a redox reaction is shown. Which species is being oxidized in this reaction? We can see over here, if you look at tin, right, we have SN2 plus over here, right, because we have chloride, that's 2 times 1 minus, so this is 1 2 plus over here, right, the tin. And SnCl4, the tin is plus 4 because we have 4 chlorides. We have 4 chlorides over here. So the oxidation number of tin is going from plus 2 to plus 4. That means that tin 2 plus is being oxidized. Tin 2 plus is being oxidized to tin 4 plus. Right, so the answer is A. Okay, Cl minus remains the same throughout, so it doesn't change, and mercury goes from 2 plus to 1 plus. Okay, so mercury is being reduced, Hg is being reduced over here. Okay, so it's the oxidizing agent, and tin is undergoing oxidation, it's the reducing agent. .6 moles of hydrogen gas and 2 moles of iodine vapor are placed in a reaction vessel, which is then sealed and maintained at constant temperature. The equation for the reaction is shown. At equilibrium, 3.2 moles of hydrogen remain. All reactants and products are gaseous. What is the value of Kp under these conditions? So over here, what we can do is we can use an ice table, right? We have H2 plus I2 giving us 2HI. And this, we're going to use an ice table. Okay, the ice table is for number of moles. It's for number of moles. Initially, we had 3.6 moles of hydrogen and 2 moles of iodine, right? And obviously, we had 0 moles of hydrogen iodide. At equilibrium, they said that 3.2 moles of hydrogen remained. So at equilibrium, we had 3.2 moles of hydrogen left. So then how many moles of hydrogen reacted? We know that for hydrogen, 0.4 moles reacted, right? 0.4 moles reacted. Again, the ice table is initial amount, the change in the amount, and the equilibrium amount. They've given us the initial amount and the equilibrium amount. So we know the change was negative 0.4. 0.4 moles of hydrogen reacted. So then how many moles of iodine reacted? Over here? they're reacting in a 1:1 ratio. For every mole of hydrogen, 1 mole of iodine will react. So if 0.4 moles of hydrogen react, then 0.4 moles of iodine react. So we're left with 1.6 moles at equilibrium for iodine. And how many moles of hydrogen iodide were formed? For every 1 mole of these two that react, 2 moles of hydrogen iodide are formed. So that means we had 0.8 moles of hydrogen iodide forming. So at equilibrium, we had 0.8, right? Now, if we talk about the Kp, right? For the Kp, we're going to have partial pressures. We're going to have the partial pressures. But in this particular case, what happens is this. When you look at the Kp, it's partial pressure of hydrogen iodide squared divided by the partial pressure of hydrogen times the partial pressure of iodine, right? But in this particular case, what you have is, remember, the partial pressure is the mole fraction, that's the number of moles, divided by the total number of moles times the total pressure, right? Same thing here. You have the number of moles of hydrogen divided by the total number of moles times the total pressure. And same thing here, right? You have the number of moles of iodine divided by the total number of moles times the total pressure. But now what we have over here is in the numerator and the denominator, we have the total pressure being squared, right? So that will cancel out, and you have total number of moles being squared, so that will cancel out. So at the end of the day, what you're just left with over here is, because Kp is unitless, okay, instead of the partial pressure, you can directly use the moles, because the total pressures and the total number of moles will all cancel each other out. So you don't have to use partial pressures here. That's why they haven't given us the pressure at all. You can just take the ratio of the moles, okay? So then we can say that this will simply be 0.8 squared divided by 1.6 times 3.2. And what does that value come out to? The value comes out to 0.125. So that is our Kp. I'll repeat this. Because in this particular case, the units in the numerator and the denominator were canceling each other out, what that meant was that the number of moles, the total number of moles and the total pressures were canceling each other out. So what we realize is that the ratio between the moles is the same as the ratio between the pressures. So only when Kp is unitless, you can solve for Kp without using the partial pressures. You can just directly use the number of moles. Okay. Two chemicals X and Y react together in solution to give product Z. The rate of formation of product Z at the start of the reaction was measured in 5 experiments. Using various concentrations of X and Y, the results are shown. So here we have 5 different experiments. We're using different concentrations, and we're measuring the rate of formation of Z. And we know that obviously the rate of formation will depend on the concentrations, right? Higher concentration means faster rate of formation. Which statement is correct? The rate of the reaction is directly proportional to the concentration of reagent X. So first of all, we need to look at an experiment where the concentration of reagent X is changing, right? Now, if you compare experiments 3 and 4, we're changing X and Y. So we can't really say anything about that. What about 4 and 5? Between experiments 4 and 5, you're doubling the concentration of X, whereas Y remains the same. The concentration of Y is the same. They both affect the rate, right? X affects the rate as well as Y. If you only wanna find the effect X has. So you're gonna make sure you've kept Y constant. So you've kept Y constant here, we're only changing X. If I double the concentration of X, does it have any effect on the rate? We can clearly see that doubling the concentration of X while keeping Y constant has no effect on the rate. So we can clearly see that it's not directly proportional to reagent X. And then we can easily see which statement is true. The rate of the reaction is not affected by the concentration of reagent X. So the answer here is C. Okay. But we can eliminate, let's look at the other two as well. The rate of the reaction is directly proportional to the concentration of Y. Again, over here, what you see is, here X is being kept constant, whereas Y is being doubled. If you double Y, the rate multiplies by a factor of 4. So it's actually proportional to the square of the concentration of Y. Doubling Y means the rate increases by a factor of 4. You multiply Y by a factor of 4, the rate multiplies by a factor of 16. So it's not directly proportional to the concentration, it's directly proportional to the square of the concentration. Okay, and we can clearly see that it is affected by reagent Y as well. So obviously D is also incorrect. Okay, so the answer here is C. A sample of SiCl4 is added to cold water. Which statement describes the mixture formed at the end of the reaction? Now we know that when SiCl4 reacts with cold water, right, it'll form an acidic solution. If you guys remember, the non-metal chlorides always form acidic solution, period 3 chlorides. And what it forms is it forms SiO2 and HCl. Okay, those are your products. So you're forming an acidic solution, and SiO2 is a white precipitate. So you're forming an acidic solution with a white precipitate. Okay, so the answer here is B. L and M are elements in period 3 of the periodic table. The oxide of L is a solid at room temperature. This oxide has a giant structure. The chloride of L does not react with water. Argon is the only element in period 3 with a lower melting point than M. So let's actually look at the last statement first. We can easily identify M. Okay, that's the easiest one to identify here. Which element has the second lowest melting point in period 3? You guys remember the melting point trend in period 3. If you guys remember the melting point trend in period 3, it looked like this, right? It looked like this, where we had like this, and then this, and then this, and then this. Okay, so we had argon, which was the lowest, and slightly higher than argon was, if you guys remember, chlorine, right? Sulfur was S8, right? Phosphorus was P4, and then you had silicon, which was a giant covalent structure, right? Aluminum, magnesium, and sodium. So if you guys remember, if you go across the period, right, the metals, sodium has the lowest amongst the metals, magnesium is much higher, aluminum is slightly higher than magnesium, silicon has the highest melting point by far because it's a giant covalent structure, and then you get to the simple covalent molecules. In this particular case, we know that phosphorus is slightly lower than sulfur because phosphorus has fewer electrons, whereas chlorine is lower than both. Okay, so chlorine would be lower than phosphorus and it would be lower than sulfur as well. Okay, but slightly higher than argon because it has more electrons in argon. So this trend is because of the number of electrons. So we know that element M over here is chlorine. Okay, element M is chlorine. All right, so then based on that understanding, what can we say? So that means that in our compound over here, right, chlorine is present. So it has to be C or D, right? And which of these doesn't react with water at all? Which of these doesn't react with water at all? It only dissolves in water, but it doesn't react with water. So we know that PCl5, just like SiCl4, right, undergoes hydrolysis in water. It forms an acidic solution. Hydrolysis is a type of reaction where sodium chloride only dissolves in water. It's a physical phenomenon. It's not actually reacting with water. It simply dissolves in water to give a neutral solution. So we know that the answer must be sodium chloride. And plus we know that the oxide of sodium has a giant structure, whereas the oxide of phosphorus does not have a giant structure. Okay, it's a simple molecular structure. This is a sodium oxide is a giant ionic lattice, right? A farmer requires a solid compound to raise the pH of the soil in a field from 5.5 to above 6. Which compound could the farmer use? So we want to raise the pH, we want to increase the pH. If we want to increase the pH, we have to use a basic compound, right? And we know that calcium hydroxide is basic, right? It'll increase the pH. So we can use, if you guys remember calcium oxide, calcium hydroxide, calcium carbonate, right? They're all used to increase the pH of soil or reduce the acidity of soil. So the answer here is C. Calcium nitrate is neutral, right? Ammonium is acidic. Ammonium again is acidic. So these two will lower the pH. These two will decrease the pH, okay? This will increase the pH because it's basic. Z is an anhydrous compound of a group 2 element. When it is heated, Z undergoes thermal decomposition to produce two different gases. Z has a relatively low thermal stability compared to other group 2 compounds containing the same anion as Z. What is compound Z? First of all, is it carbonates or nitrates that give us two different gases when it's decomposed? Group 2 carbonates or nitrates? We're getting two different gases from the decomposition. So it's nitrates, right? So automatically we can eliminate A and C because carbonates only give carbon dioxide as a gas, right? That's the only gaseous product in their decomposition, whereas nitrates give nitrogen dioxide and oxygen. Now, they're also saying that Z has relatively low thermal stability compared to other group 2 compounds with the same anions. In other words, it has relatively low thermal stability compared to other nitrates. Now, which of these nitrates is less stable thermally? Which of these decomposes easier? If you guys remember the trends in thermal stability down the group, what happens to the thermal stability down the group? The thermal stability increases, right? Increases down the group. So we know that barium nitrate is much more thermally stable. And because Z has a relatively low thermal stability, right, it decomposes easily. It requires a lesser temperature to decompose, so it must be magnesium nitrate. Which row gives mixtures that both result in the oxidation of a halide ion? We'll go through the options one by one, okay? But it'll serve as good review as well. Silver nitrate and NaCl. Is there any redox reaction taking place here? We get silver chloride, is just a precipitation reaction, but there's no redox reaction here, right? If you guys remember, this will just give us AgCl. So there's no redox reaction here. This is a redox reaction, right? This is a redox reaction. Sulfuric acid will oxidize iodide, but not both. Both reactions won't result in oxidation. What about bromine and chloride? Can bromine oxidize chloride? Can bromine oxidize chloride? We know that bromine cannot oxidize chloride because chlorine is a much stronger oxidizing agent. So it wants to remain an anion more than bromine does. Chlorine prefers being the anion more than bromine does. So bromine won't be able to oxidize chloride. Bromine can, however, oxidize iodide, right? So we know that bromine can't oxidize chloride, but it can oxidize iodide, okay? Now, if you look at C on the other hand, chlorine can oxidize bromide as well, okay? Chlorine can oxidize bromide, but bromine can't oxidize chloride. But what if you look at C, if you look at the second reaction, this is an elimination reaction, right? Halogenoalkane with sodium hydroxide and ethanol. This is not a redox reaction. So again, this is not the reaction. So the answer here must be D. The answer here must be D. Okay. Bromine can oxidize iodide. We know that because bromine is a stronger oxidizing agent than iodine, right? So this will take place, right? We'll form iodine and bromide. So over here we can clearly see that the halide iodide is being oxidized, right? The iodide is being oxidized. And we also see that we know that concentrated sulfuric acid can oxidize bromide as well, right? Sulfuric acid will undergo reduction to form sulfur dioxide. Sulfuric acid will undergo reduction to form sulfur dioxide, and we're also going to form bromine over here, okay, amongst other things. So this will also be a redox reaction. So both of these are possible. Chlorine gas is widely used to treat contaminated water. When chlorine is added to water, which chemical species present is responsible for killing bacteria? So if you guys remember, when chlorine reacts with water, right, it forms HCl and HClO. Okay, this is what's responsible for killing bacteria, right? The chlorate 1 ion. The chlorate 1 ion. Okay, this is called the chlorate. This is called chlorate 1. This is what's responsible for killing bacteria. Okay, so the answer here is D. Okay, we're forming chlorate 1 ions that are responsible for killing the bacteria. What is an environmental consequence of the uncontrolled use of nitrate fertilizers? When we use nitrate fertilizers, right, it causes eutrophication, right, which ultimately results in lowering of oxygen levels in bodies of water, right? That results in the death of. All right. Ammonia gas, NH3, and hydrogen sulfide react together to form the salt ammonium sulfide. Ammonium sulfide dissolves in water to produce an orange alkaline solution. It's alkaline because of NH3, right? Hence, this is dissolving in water to give us an alkaline solution. The addition of NaOH to this solution produces a gas X. The addition of HCl aqueous to a separate portion of the solution produces a gas Y. X and Y could represent different gases or identical gases. What are the identities of X and Y? So they're saying over here that the addition of NaOH to this solution produces a gas X, right? So let's first identify X over here. Now, when we talk about NaOH aqueous, which of the species present here reacts with NaOH aqueous? You have ammonium ions, you have sulfide ions, you have these ions over here, right? These SH minus ions, and you have ammonia. And ammonia is obviously alkaline, so it doesn't react with NaOH aqueous at all, right? We don't really care about ammonia. But which of these species will react with sodium hydroxide? Sodium hydroxide is an alkali, right? It's basic. So which will react with sodium hydroxide here? Which one do you think will react with sodium hydroxide? We know that ammonium ions will react with sodium hydroxide, right? Because ammonium ions are acidic. And we know that ammonium ions react with sodium hydroxide to form NH3 and H2O, right? We have a neutralization reaction. Ammonium is acidic, sodium hydroxide is alkaline, right? Basic. So then what gas is being produced here? When ammonium ions react with sodium hydroxide, we produce NH3, right? So that's one. Now, which of these species will react with HCl to produce the gas Y? When we react with HCl, a gas Y is produced. Now, if you think about it, right? When these guys over here, they gain a proton. When they gain a proton, what will they form? This guy, if it gains 2 protons, or if this guy gains a proton, what will it form? They'll both form what? If they react with HCl, they will form hydrogen sulfide, right? They will form hydrogen sulfide. So the answer here is C, right? The anions here can react with acids. They can gain protons. They can accept protons to form hydrogen sulfide, whereas the ammonium ion here can react with sodium hydroxide to form ammonia. So the answer here is C. Compound P is treated with an excess of hydrogen gas in the presence of a nickel catalyst. The product Q is fully saturated. What is the number of chiral carbon atoms in the product Q? So what we're doing here, since we're reacting this compound with hydrogen gas in the presence of a nickel catalyst, and we're getting a saturated compound, we're simply doing hydrogenation of alkenes, right? So we're basically just adding hydrogen gas to each of the carbon-carbon double bonds. So it leaves us with only single bonds over here. Now, this is our final product. How many chiral carbon atoms are present in this product over here? Again, we had compound P that has double bonds. We treated it with hydrogen in the presence of a nickel catalyst, and now we got rid of the double bond, right? We've added hydrogen to each of these double bonds, right? Hydrogen gas. So that means now we don't have these double bonds anymore. We have a saturated product Q. So now we don't have P anymore. We have compound Q over here, okay? How many chiral centers are present over here? So is this one a chiral center? This carbon over here? We have a CH3, this, and then an H, right? It's asymmetric with respect to this one. So this is one chiral center that we have. Are these chiral centers? These CH2s over here? No, obviously not, right? What about this one? Yes, okay. What about this one? It has two identical CH3s on it. Is this one a chiral center? No. Okay. What about this one? Again, this is a chiral center, right? Okay, so that's 3 so far. Then again, we have CH2s and CH2 here. We have a CH2, CH2. You have CH2, CH2, CH2. So you can get rid of all of these. Now, is this one a chiral center? Yes, again. So we have 4. This one, again, yes. So then we have 5, right? So the total number of chiral centers over here is 5. So the answer is B. All right. Hexadeca-10,12-diene 1-ol is produced by silk moths from hexadecanoic acid in a 3-step enzymatic process. Okay. So what we have is, we have, in the presence of an enzyme, we're converting this carboxylic acid into this compound over here. That's a diene with an alcohol group, right? Diene monol. This is our final product. Which row contains the correct descriptions of the 3 steps? Now, if you look at the first step over here, what we have over here is, in the first step, we're removing hydrogen. Now, if you guys remember, the addition of hydrogen was called what? The addition of hydrogen was called reduction, right? When we converted a double bond, if you guys remember, we added H2. So the reverse reaction, step 1, would be called oxidation, right? So step 1 can be classified as an oxidation reaction. Okay, so that leaves us with C and D. Step 2, on the other hand, what you're doing is you're making another double bond. So again, what are we doing here? Again, from double bond to alkane, from alkene to alkane, it's reduction. If you guys remember, right? Hydrogenation, addition of hydrogen. So from alkane to alkene, it is again oxidation, right? It's again oxidation. And in step 3, what we're doing is, in step 3, we're converting a carboxylic acid into a primary alcohol. So that type of a reaction is called a reduction reaction, right? So then we have reduction taking place over here. Okay, the answer is D. Compound X can be converted into compound Y in a single step. What could be the identity of X? Now over here, we know that X was an alkene. Okay, X was an alkene, and it was oxidized using hot concentrated acidified KMnO4, right? It was oxidized using hot concentrated acidified KMnO4, right? It was strong oxidation of alkenes. You ruptured the double bond. Now, the product that we have over here is compound Y, okay? We have compound Y over here. Now, the first question that I have is, right, X is a cyclic alkene. We broke that double bond, we ruptured the double bond, and it resulted in the formation of compound Y. So the first question that I have over here is, which 2 carbon atoms were initially bonded in the alkene itself? Which 2 carbon atoms were initially bonded but double bonded before the double bond was ruptured? I've numbered these carbon atoms. So which 2 carbon atoms were initially bonded by a double bond? We can clearly see that on carbon 1, we have a carboxylic acid group, a carboxyl group, and on carbon 5, we have a ketone, right? We have a carbonyl. So that means carbons 1 and 5 were initially bonded. That's where the oxidation took place. On carbons 1 and 5, we have these oxidation products, right? We have carboxyl group and carbonyl group. So that means that carbons 1 and 5 were initially bonded together. Carbons 1 and 5 were initially bonded together. So then, how big was our ring? These 2 were initially bonded to each other, and then the ring broke. So our ring, is it a 5 carbon ring or a 6 carbon ring? If carbons 1 and 5 were initially bonded together, that means that we have a 5 carbon ring, right? We have a 5 carbon ring. Good, right? So we have a 5 carbon ring. Okay, so that again eliminates C and D as possibilities. Okay, now if you guys remember, for a carboxylic acid to form, right, let's call this one carbon number 1, where I've labeled it over here, right? So we know that for a carboxylic acid, the carbon has to be, the carbon on the carbon-carbon double bond, the carbon on the carbon-carbon double bond has to be bonded to 1 hydrogen and 1 carbon-containing group, right? Now we already know that it's bonded to a carbon-containing group, that's the ring itself. So that means that this has a hydrogen on it, right? So that's fine. And what about a ketone? Carbon 5, right? Carbons 1 and 5 were initially bonded to each other by a double bond. Again, what happened was, when we broke this ring, right, we formed an acid group here, and we formed a ketone group here. So then carbon number 5 is also bonded to what? Carbon number 5 must be bonded to a, if you're forming a ketone, right, on a carbon-carbon double bond, if you're forming a ketone, that means that the carbon atom is bonded to 2 carbon atoms, and we can clearly see that here. Carbon number 5 is bonded to a methyl group. So that means carbon number 5 is bonded to a methyl group over here, right? So we've seen that so far. Okay, now there's also another methyl group on carbon number 2. There's also a methyl group on carbon number 2. That would be this carbon over here, right? The carbon next to the carbon that produces the acid. This carbon gives us the acid, and on the neighboring carbon you also have a methyl group. Okay, so I'll repeat this. Okay, first of all, we have a 5 carbon ring, because we know that these two carbons were initially bonded. When that double bond ruptured, we produced a ketone and an acid, right? Now, the carbon that produces the acid had one hydrogen bonded to it. That's from strong oxidation of alkenes, right? And we know that the neighboring carbon had a methyl group. Okay, and we know that carbon number 5 is bonded to this ring, and it has a methyl group on it, because this carbon must have been bonded to 2 carbon atoms for us to get a ketone over here, right? So the answer over here is A, right? This is the carbon that gave us the acid. On the neighboring carbon, we have a methyl group, and on this carbon, we have another methyl group over here, right? This is what gave us the ketone. This is what gave you the ketone, and this is what gave you the acid group. Okay, so the answer here is A. Again, because we have the oxidation products on carbons 1 and 5, they were initially bonded to each other, so you had a 5 carbon ring. Okay, the carbon that gave us the acid, on the neighboring carbon you had a methyl group, and the carbon that gave us the ketone, that's carbon number 5, the way I've labeled it, okay, that was also bonded to an additional methyl group, right? This guy over here. So therefore the answer is A. Methane and bromine react by free radical substitution. P and Q are involved in the reaction mechanism. P and Q are both involved in propagation steps as reactants and are both involved in termination steps as reactants. What could be P and Q? Now, first of all, is H ever involved in the reaction at all anywhere? Whether it's propagation, whether it's termination, whether it's initiation? No, right? It's not. Okay. What about bromine radicals and CH3 radicals? Are they involved in propagation reactions? If you guys remember, bromine radicals are involved in propagation, right? And so are CH3 radicals, right? They're involved in propagation as well. They're involved in propagation as well as reactants. So we can clearly see that bromine radicals are involved and CH3 radicals are involved in propagation, right? And they can also be involved in termination, right? They can combine with each other. In termination as well, right? To form CH3Br. So they're involved in both. They're both involved in propagation, and they're both involved in termination. So the answer over here is this termination, this propagation, right? The answer here is B, right? They're both involved in propagation and termination. Okay. Molecules can never be involved in termination, because in as reactants, because for termination you need 2 radicals. So you can already eliminate C and D. Okay, because you have molecules here. Molecules will never be reactants in termination. In termination you need 2 different radicals. Okay, so the answer is B. A few drops of 2-bromopropane were placed in a test tube. An equal volume of aqueous silver nitrate was added. A precipitate was formed. The experiment was repeated with 2-iodopropane. Which row is correct? So what's the color of the precipitate when silver nitrate reacts with bromopropane? Do you get a yellow precipitate or a cream precipitate? Silver bromide is, right? Silver bromide is the precipitate, and silver bromide is a cream precipitate. Okay, yellow would be silver iodide. So we know that it can't be B or D, it must be A or C. Okay. Which has a faster rate of reaction? So do iodoalkanes react faster or bromoalkanes? When we talk about the rate, we know that iodopropanes will react faster, right? Iodopropanes will react faster because the carbon iodine bond is weaker than the carbon bromine bond, because iodine is a much larger atom, right? Greater bond length, hence weaker bond. Weaker bond means lower activation energy and faster rate of reaction. So we know that iodopropane will react faster with silver nitrate. Okay, so the answer here is C. Sodium methoxide reacts with 2-chloro-2-methylpropane in a nucleophilic substitution reaction. The nucleophile is a CH3O- ion. Which row is correct? So the first thing is that we have to identify the intermediate or the transition state as well as the product, right? So the question here is this. The question here is this. Do we have an SN1 reaction or an SN2 reaction? So what we have over here is this. We have 2-methyl, right? We have 2-chloro, 2-methyl propane. So this is our initial reactant. So what type of halogenoalkane is this? Is primary, secondary, or tertiary? The carbon with the chlorine is bonded to 3 other carbon atoms. So this is a tertiary halogenoalkane. So then, tertiary carbocations, are they favored or are they more favored or less favored? Tertiary carbocations are more favored, right? So that means this will undergo what reaction? What mechanism? Will it be SN1 or SN2? It will undergo the SN1 mechanism. This will undergo the SN1 mechanism, right? We're going to form a carbocation intermediate. We're going to form a carbocation intermediate. So in the first step, what will happen is that this will break off, right? This will break off, and you're going to form the carbocation intermediate, right? And when you form the carbocation intermediate, that carbocation intermediate looks like this, right? This is our carbocation intermediate. So then, right, the answer is either A or B. It can't be C or D because we know it's an SN1 reaction, right? Because it's a tertiary halogenoalkane. We're going to form a tertiary carbocation intermediate. And then what's the final product here, right? The nucleophile is the CH3O minus ion. So in the second step, what will happen is, in the second step, the CH3O minus will end up bonding to this carbon, right? And we'll be left with our final product, which is what? Our final product will be this guy over here, right? This carbon is bonded to 3 CH3, so we have CH3 thrice C, right? And then this will also be bonded to an OCH3, COCH3, okay? So then the answer here is A. Alcohol X reacts with concentrated sulfuric acid to produce a mixture of products. 2 of the products are structural isomers of each other. What could be X? So what type of a reaction is taking place over here when an alcohol is reacting with concentrated sulfuric acid? So for example, let's look at A, right? You have hexane 2-ol. So we have a 6-carbon chain, right? And this is reacting with concentrated sulfuric acid in the presence of heat. You heat it strongly, okay? So then the reaction that you have over here is elimination, right? You're dehydrating the alcohol. If you guys remember, you can use concentrated sulfuric acid and heat, or you can use Al2O3, alumina, and heat, right? So what happens is that you remove an OH and an H from the neighboring carbon. So either you can remove the OH and this H over here, in which case you're gonna get hex 1-ene, right? That's 1, 2, 3, 4, and then 5, 6, right? Or instead of removing this hydrogen, you can remove this one on the other carbon, on the middle carbon, right? Carbon number 3. You can remove this hydrogen as well, in which case you're gonna get hex 2-ene, right? Which is this guy. If you remove this hydrogen, then you're going to make a double bond here. So you can either make the double bond here or you can make the double bond here, right? And hex 2-ene could be cis hex 2-ene or trans hex 2-ene, right? You could have cis hex 2-ene or trans hex 2-ene, right? So these are the 3 products that we're making. But are we making any structural isomers over here? We have hex 1-ene, and hex 2-ene, right? Trans hex 2-ene and cis hex 2-ene. So are these structural isomers of each other? The answer is yes, right? The answer over here is yes. We're making hex 1-ene and we're making either cis hex 2-ene, right? We're making either cis hex 2-ene and or trans hex 2-ene. So we know that hex 1-ene and hex 2-ene are position isomers of each other, right? They're position isomers of each other. So that means that they are indeed structural isomers of each other. These 2 are structural isomers, or you can say these 2 are also structural isomers of each other, whereas these 2 are geometric isomers of each other. So in this reaction, you are making structural isomers, right? They're position isomers here, hex 2-ene and trans 2-ene, hex 2-ene and hex 1-ene, sorry, right? But hex 2-ene is actually 2 different things. It could be cis or trans hex 2-ene. So in this particular case, you're making structural isomers as well as stereoisomers. Okay, so the answer is A, right? Two of the products are indeed structural isomers of each other. Which reaction will form a strong organic base? Ethanol and acidified sodium dichromate. Does this form a base? Ethanol with an oxidizing agent. Here we have an acidified oxidizing agent. So ethanol will simply make ethanoic acid, right? If this was alkaline conditions, if we, for example, we use alkaline KMNO4, then we're going to make a base. Okay, but here we don't have alkaline conditions, we have acidic conditions. So we're just making the carboxylic acid. What about ethanol and aluminum oxide? Here we're making an alkene, right? Here we're making an alkene. We just saw that reaction, right? Alcohols with aluminum oxides, right? Here we're making ethene. So that's not it. What about ethanol and sodium? Ethanol and sodium. When ethanol reacts with sodium, right? When ethanol reacts with sodium, it forms this, right? When it reacts with sodium, it forms CH3, CH2, O minus, Na plus, and hydrogen gas, right? If you guys remember, sodium is a test for the OH group. This is a base. This ethoxide ion is basic. The ethoxide ion is basic. Okay, so here you're actually making an organic base. Even though ethanol is not an acid, but because the H plus over here is reduced, right, to form hydrogen gas, right, what you end up making is this anion, and this anion is an organic base. So the answer here is C. Okay, ethanol and sodium react together to form the ethoxide ion, which is an organic base. Which reaction mechanism for the formation of C2H5CHOHCN is correct? So this is a nucleophilic addition reaction. This is a nucleophilic addition reaction. Okay. So in part A, is the first step of the mechanism correct? The Cn minus ion is the nucleophile. It donates its electrons to this delta plus carbon, right? And you form this anion intermediate. Okay, the first step is correct. What about the second step? Is the second step correct? The electrons going from the H plus to the oxygen? No, the second step is incorrect, so it can't be A. What about B? Is the first step correct? No, the first step isn't correct in this case. What about C? Is the first step correct? The first step over here, you have a delta minus carbon. No, right? It's a delta plus carbon. So this is also incorrect, right? It should be a delta positive carbon, right? So then you're left with D. And we can clearly see that D is correct. Nucleophile, delta positive carbon, arrow from nucleophile to that carbon. And then in the second step, electrons from the oxygen to the H, right? This H is HCN. You can say H plus or you can say HCN. It's the same thing, okay? So what we have over here is, this is also correct. So the answer here is D. The synthesis shown may be used for the production of propan-1-ol. Which row gives the correct reagent for steps 1 and 2? So we're converting this nitrile eventually into a primary alcohol. The CN is being converted into a CH2OH. The C triple bond N is being converted into a CH2OH. So what do I need to first convert? What do I first need to convert the cyanide to, the nitrile to? First, I'm going to convert the nitrile to what? First, I'm going to convert the nitrile to a carboxylic acid. Good. And then the carboxylic acid can be reduced to form the primary alcohol. Now, which of these reducing agents can reduce a carboxylic acid? Only one of these reducing agents can reduce a carboxylic acid. That reducing agent is lithium aluminum hydride. For step 2, from carboxylic acid to primary alcohol, you can only use LiAlH4 in dry ether, right? Anhydrous LiAlH4. So that means in the first step, what we're doing is we're hydrolyzing the nitrile to form a carboxylic acid. And the second step, we're reducing the carboxylic acid with LiAlH4 to lithium aluminum hydride to produce a primary alcohol. So the answer is B. Okay. The molecular formula of Z is C4H8O. The infrared spectrum of Z is shown. What could be Z? Okay. So now we have to identify compound Z based on the infrared spectrum. Okay. All right. So if you look at the table that we have for the infrared spectrum values, right? Let's first look at this peak over here. Here you have a peak at around 1650. You have a peak at around 1650, okay, or 1640 wave numbers. So what is that peak? Is it a C double bond O, or is it an alkene? Right? We know that it's not a carbonyl or a carboxyl group. It's not a C double bond O, because that would be slightly higher and it would be a bigger peak. Okay, so this peak over here at around 1640 is because of the carbon-carbon double bond. All right. Then what we have is we have the CH peak over here. We have the CH peak over here. This is because of the CH bond, and this is at 2850 to 2950 wave number. So around 2900. And the last peak that we see is the OH from the alcohol. This peak over here is the OH from the alcohol group. Okay. The reason why it's from the alcohol group is because it's around 3400 wave numbers, okay, which is consistent with the range. It's around 3400, right? So it's in the range 3200 to 3600. And if it was from an acid, if it was a carboxylic acid peak, it would be a much broader peak. Okay, the peak would sort of look like this. It would be a much broader peak like this. Okay, so carboxylic acids have a much broader peak. So it's not a carboxylic acid OH group. It's an OH group from an alcohol. Okay, so then which of these could be Z then? We have a carbon-carbon double bond and we have an OH from an alcohol. The answer here must be D. Okay, the answer here must be D. Okay. If you're unsure about the C double bond O, you should still be certain that the answer is D, and I'll tell you why. The answer can't be A. Like, for example, if you thought this was C double bond O, if someone did even identify this as C double bond O, there's no OH peak in A, right? And it can't be C, because even if this was C double bond O, we know that the carboxylic acid OH peak doesn't look like this. It's a much broader peak, so it can't be C either, right? And it can't be B, because B doesn't explain this peak at all. So this must be a C, it must be a carbon-carbon double bond, okay? And therefore the answer is D.